What comes to your mind when you think of a family gathering? I am already dreaming of a sunny garden party with good food and drinks and of course lots of laughter with your cousins. While you're chatting with your aunt and uncle, they ask how your PhD is going. You smile and you say, "Good, thanks." They remember you're working on energy and soon the real question comes. We are thinking about renovating our house and we want a more climate-friendly energy system. We are still heating with a gas boiler and we are considering installing solar panels. But there are so many options and everything is expensive. Plus, does it even make a difference for us just a small house to renovate? What should we do? It's not the first time you get this question, and luckily, after 3 years of PhD, you have some answers to help them out. But first, you reassure them. Their actions do matter. Households are responsible for 26% of Europe's final energy use, of which the majority is for heating, so space heating and domestic hot water. In fact, 18% of Europe's final energy use comes from the direct fossil fuel combustion in households. And if you include the tertiary sector and part of the transport sector linked to the buildings, that number is even higher. So, replacing fossil fuels in your own house really makes a difference. Luckily, many energy technologies already exist. Solar panels and solar thermal collectors can harvest solar energy to produce electricity and heat respectively. Heat pumps use electricity to upgrade heat from the air, water or ground. Batteries allow for storing renewable electricity for later use, and big water tanks serve as a thermal storage. On a larger scale, wind turbines generate electricity and then transport. Electric vehicles are stepping in to replace traditional combustion engine cars. However, the big question remains: what should we install given our two main goals? First, we want to reduce our climate impact, and second, we want affordable solutions. So, we are looking for the solutions with the lowest CO2 emission reduction cost. Fortunately, we can rely on our simulation-based integrated strategy. By combining models of the energy system with optimal control, we can compare the CO2 emission reduction cost of different energy systems in a fair and consistent way. Let's start with the models, and we begin with your house. We model the building as is, so we make a mathematical description based on the building's geometry, the constructions of the walls, the floors, the roofs, the windows, and the physical properties of the materials. Next, we connect the building to the energy system, and this includes everything to supply space heating, space cooling, domestic hot water, and electricity for the plug loads or electrical appliances. We model all energy services because we want to incorporate the synergies between all energy carriers. We use detailed and non-linear physics-based models to capture the real behavior of the system. We don't model thermal power as a single quantity, but instead we model mass flow rates and temperatures, because a thermal power at the wrong temperature is useless. We don't use demand profiles, but we use dynamic models to exploit all flexibility in the entire system. For instance, you can use the thermal mass of the buildings or the water in the hydronic circuit to shift demand in time. This is known as demand response and supports a better match between energy supply and energy demand. Many of these key aspects are simplified or neglected in the state of the art. To operate the system, we integrate an optimal predictive control strategy that takes the future into account for the current control actions. The optimal controller minimizes an objective function while taking into account the constraints. We minimize climate impact and maximize energy efficiency while maximizing comfort for the occupants. After adding information on the boundary conditions, we can perform annual analyses and compare the CO2 emission reduction costs of different energy systems. Let's take a look at the house of your aunt and uncle. They still have a gas boiler in place for space heating and domestic hot water. The boiler emits almost 4 tons of CO2 per year, which corresponds to 36,000 kilometers by car, or the CO2 absorption of 180 trees. Only a minor part is linked to the electricity consumption. For this system, they pay around 3,500 euros per year, including the annual investment cost for the entire system with a small solar PV installation. So, the first step is to eliminate the emissions from the gas boiler by replacing it with a heat pump. This switch reduces emissions by 94%, but also increases costs by 46%. Combining this emission reduction with cost increase leads to an emission reduction cost of 420 euros per ton of CO2 reduced. Unfortunately, the annual investment costs have increased significantly, but fortunately, collective systems can offer benefits for this. Your aunt and uncle could collaborate with their neighbors in a small energy community by installing a collective heat pump and sharing the heat via a district heating network. In this energy community, the shared investment leads to much lower costs, bringing down the emission reduction cost to 180 euros per ton of CO2. That's why I strongly recommend considering a collective solution with your neighbors. As the entire energy system is electrified, battery energy storage seems an interesting technology to store excess renewable electricity for later use. However, the opposite is true. Battery energy storage only reduces emissions in summer to cover the plug loads during nighttime. In winter, there is less excess renewable electricity, and if there is, it's stored immediately in the building's thermal mass thanks to the optimally controlled heat pump. This way, energy losses in the battery energy system are avoided. This effect only becomes visible when we use dynamic, flexible building models instead of static, predefined demand profiles. We have compared both approaches, and in the case of static demand profiles, battery energy storage appears more interesting, simply because it's a sole source of flexibility. The very small emission reduction in absolute terms and the high investment of battery energy storage lead to an emission reduction cost of 5,130 euros per ton of CO2, which is more than 10 times the emission reduction cost of electrifying a gas boiler. Aan tafel! The food is ready and everyone is hungry. Of course, there is much more to tell about, but for now you make your aunt and uncle happy with 2 take-home messages. First, we have a method that allows us to easily model and compare different energy systems. The method includes all energy services, detailed physics-based models, and an optimal predictive control strategy to capture the system's real behavior and exploit all inherent system flexibility. This approach can support an effective energy transition. Second, the gas boiler is responsible for most of your emissions at home. So electrifying heating with a heat pump is the first step to drastically reduce your CO2 emissions and the local emission of pollutants. If you collaborate with your neighbors in an energy community, the emission reduction cost comes down to 180 euros per ton of CO2 reduced. By the way, this cost is in the range of the expected emission tax Europe will implement in 2027. So, a collective heat pump is a future-proof track. The path is clear. Electrify, collaborate, and make the future happen together.